Hello there, my name is Waithera Wangui and I'm going to be covering aggregates in domain-driven design today. I know it's been so long, but I'm finally back. So what is an aggregate? An aggregate is one or more domain objects that need to stay consistent as a whole. They're treated as a whole. This can be many entities, this can be many value objects. I'll add an attachment to entities and value objects. I've made consistent the same, so you can go back and get to read more about it and understand what I'm talking about when I say entities or when I say value objects. So for instance, I have my student, and within this student, I have the name, I have a birth date, I have extracurricular activities for this student, I have the student class, I have the duties they're supposed to do. So all these are components that work together for a student object. So these can go to the same aggregate. So in this case, we have entities within this aggregate and we have value objects, for instance, date of birth. So what happens when you delete or make a change? Everything needs to stay consistent when you make any change. Think about aggregates as having a life cycle. They are created, they have a life in between creation and death, and then they're deleted. So that's how they work. They do have a life cycle. We'll get to learn more about this when we talk about factories and repositories in an upcoming course that is coming soon. So even when considering an isolated transaction, the web of relationships in a typical object model gives no clear limit to the potential effect of a change. Because of this, you need to really create it you need to be really intentional in creating your aggregate, but we'll learn more about what I'm saying soon. It is not practical to refresh every object in the system, just in case there's some dependency. So let me explain what I mean with all this. When I create something or I have an object, every time, for instance, I delete a student, I'll delete information like the student's date of birth, or I'll delete, let's say, let me talk about something like the address. I delete the address. In this case, let's say this address was pointing, like other students were pointing to this address. That means I've deleted an object that was actually being used by other people. Then we have a case of them pointing to null objects that don't exist. Or even in the cleanup, there's no clear definition of how much we can clean up after ourselves once we delete something. So these are the cases that lead us to design aggregates in the first place. The problem is acute in a system with concurrent access to the same objects with multiple clients. You can imagine why this is the case if you're already struggling to deal with an object on its own. So you can imagine what happens when many more people are actually concurrently accessing it at the same time. So we don't need to make sure it's always consistent every time a change is made. We have to prevent simultaneous changes to interdependent objects, and we need to be aware to not get the scope wrong because it will have very serious consequences. How do we know where an object made up of other objects begins and ends? So how do we know where it begins, where it ends? How do you know how big it is, how small it is? What affects it? What are the rules that define it? There are various ways to model aggregates incorrectly. We'll look at how we can actually mess up when creating aggregates. For one, we can make them too big. We don't want to do this. We want them, just like when designing microservices, when designing aggregates, we want them to be just big enough to handle everything it needs to handle. I know it's really big. I am forgetting there's a definition I'd like on the same way. It's like not too big, not too small, just enough. We need it to be just enough. So making it too large in this case is an issue. And also, equally as important is to be aware to not make it too small, because we're stripping all aggregates bare. We are stripping our aggregate bare, failing to protect true invariants. I've talked about a new term here called invariants. Let's find out what invariant means. An invariant is a business rule that must always be consistent within this student. Every time I make a change, it should always be left in a consistent state. For instance, let's look at maybe different classes. When I change the class, it needs to be a valid class that I've changed this student to, such a thing. It's consistent, it's complete. It will involve relationships between members of the aggregate within this aggregate. A properly designed aggregate is one that can be modified in any way required by the business, with its invariants completely consistent within a single transaction. So we've added a new part to it here within a single transaction. This is to say that we should always make our changes strongly consistent. Make sure that we leave it in a consistent state. We'll talk about other ways of having consistency, but in this case, within the aggregate, any changes made need to be strongly consistent, immediately consistent. Aggregates tighten up the model itself by defining clear ownership and boundaries, avoiding a chaotic, tangled web of objects, thus maintaining integrity in all phases of the cycle. Another definition of an aggregate, they're really the same, is it is a cluster of associated objects that we treat as a unit for the purpose of data changes. Each aggregate has a root and a boundary. We do have a boundary, and the purpose of the boundary is to define what goes inside the aggregate. Now let's go to the root. We've said it does have a root and a boundary. What is the root and what is the role of this root? The root is a single specific entity contained in the aggregate. This has a global identity and is ultimately responsible for checking invariants. We mentioned about something called a root. Every aggregate must have an aggregate root. When I started out, I talked about an aggregate containing entities, containing value objects. Once you have all these, you still need to decide which entity ID will be serving as a aggregate root. For instance, coming back to the student, I'll give an example of this in a diagram in a few. We have decided, for instance, the student ID is our aggregate ID, our aggregate root. So every time we need to access anything within the student aggregate, we have to go through the student ID and no other way. This also goes to the database level. Again, at the key of it all, at the root of it all is a problem with the model if we are finding ourselves trying to access details without going through the aggregate root. Entities inside the boundary have local identity, unique only within the aggregate. For instance, I mentioned about having things like duties inside the student aggregate. We can have maybe details of the books the student has and book IDs. These are elements specific to the student within the student aggregate, and that a local identity is there, only unique to this aggregate. We won't go accessing the books directly, we'll go through the student. For instance, this is just an example. It may not make sense, but it is just an example. Of course, when you're designing for your own system, you look at your own aggregates and formulate them. You'll identify which one is a local entity and which one does qualify to be the aggregate root in this case. Nothing outside the aggregate boundary can hold reference to anything inside except through the root entity. The root entity can hand references to the internal entities to other objects, but those objects can use them only transiently and they may not hold on to the reference. There will be cases where outside aggregates want information that is actually inside these aggregates, like the local entities, for instance, or value objects. In this case, again, as I mentioned, go through the aggregate root, get what you need, you're given that, use it, and then after that, you won't have access to it again. When you need it, you'll come back for it the same way. The root may hand a copy of a value object to another object, and it doesn't matter what happens to it because it's just a value and no longer will have any association with the aggregate. You can think of an aggregate as a consistent boundary. Everything within the boundary should be consistent immediately a change occurs. I have mentioned this about it needing to be strongly consistent every time a change happens within the life cycle of the aggregate. The root is the only member of the aggregate that outside objects are allowed to reference, although objects within the boundary may hold references to each other. I did mention that. So let's look at an example using the student. We do have an aggregate root here, which is a student ID. We have the student date of birth, which can be a value object in this case because it does qualify to be a value object. Again, learn more on value objects on a video I've done on the same. Learn more on entities on a video I've done the same. So we have a student class, we have student duties, we have student extracurricular activities, and within these, for instance, extracurricular activities, we can have activity ID and details. Let's say hockey, ID of the activity. We can have maybe the tools used, like a hockey stick, blah blah blah, depending on how you model it. This is just an example off top of my head. Cluster the entities and value objects into aggregates and define boundaries around each. Aggregates mark off the scope within which invariants have to be maintained at every stage of the life cycle. I've mentioned this a lot, that aggregates do have a life cycle, so that's just information you need to know. And now that I've mentioned life cycle, we will learn more about the life cycle of an aggregate when we cover factories and repositories, in the creation, in the fetching details of this aggregate, in the deletion. All these goes to show that it does have a life cycle. Entities other than the root have local identity, but that identity needs to be distinguishable only within the aggregate, because no outside object can ever see it out of the context of the root entity. Only aggregate roots can be obtained directly with database queries. This is something I've mentioned. Even when doing database queries and I want details of games this student is playing, I will still need to go through the student ID. All other objects must be found by traversal of associations. This is something I've mentioned, so I hope that's clear. Objects within the aggregate can hold references to other aggregate roots. At the end of the day, this aggregate root does not exist and operate on its own. It will need information from other, and others will also need information from it. Because of this, you can still point to other aggregate roots, in other aggregates. For instance, maybe there is a whole other aggregate called class that now contains more details and everything pertaining a class in a school management system. So the student may have a reference to a class ID in this case to tell me this student belongs to this class and this is a class ID, and then it points to that. It doesn't specifically have all the details of the class, but it now has a reference to the class ID so that we know what class we're referring to in this case. A delete operation must remove everything within the aggregate boundary at once. I've said this, it always needs to stay consistent. So every operation, whether it's a creation, whether I'm adding new things, of course, you don't make a change when retrieving details, but yeah, even retrieval and deletion needs to always leave it consistent. There are no outside references to anything but the root. Delete the root and everything else will be collected. When a change at any object within aggregate boundary is committed, all invariants of the whole aggregate must be satisfied. And lastly, any rule that spans aggregates will not be expected to be up to date at all times. This is where something called eventual consistency comes in. I have done my change within my aggregate, but I've done a change that may impact something else, and I need to send a message to this other aggregate to tell them to effect the change. I don't need to ensure that this change is effected immediately. It's none of my business. All I'm responsible for is, for instance, sending a message to this other aggregate to tell it to effect the change. So because of this, we don't expect it to be strongly consistent. We expect it to be eventually consistent. Eventually, you will have these changes within a specified time, but not immediately it has happened. Because since you have everything outside, this boundary is irrelevant to the aggregate. We don't think about it. It's none of our business. A properly designed aggregate is one that can be modified in any way required by the business, with its invariants completely consistent within a single transaction. Now, that's an aggregate. Let's listen to this. A properly designed bounded context modifies only one aggregate instance per transaction in all cases. I've introduced another term here called bounded context. Actually, I've made a video on the same. Go back and look at it and get to know more about what I mean when I say this. But ideally, leave everything consistent, and like for every transaction you make, leave it consistent. I've mentioned this, use eventual consistency outside the boundary. And yeah, that's it on aggregates. Feel free to ask more questions. I would make an extra video on this if it's not clear. And I think that covers it for today. My name is Waithera Wangui for Kodarasa. I'm back to producing these videos. I know it has been a year-long hiatus from this, but I'm finally back. I felt sick, but I'm now in a good state, and yeah, I'm back. So expect more videos. Like and subscribe and comment. I'll be interested to know what I could improve on, what you feel I've left out, or what you like about it. Anything. So feel free to leave a message, a comment on the video. And thank you. Until next time, bye.